Postmen, as part of the transport and logistic branch of industry, are facing a lot of challenges. Cities are growing bigger and bigger. Along with it, the volume of traffic increases. Additionally, more and more packages have to be delivered while having a lack of persons who are able to do the job. These are all factors that make the daily job of a postman hard and stressful. In general, there is no value creation while the postman is driving the vehicle to reach the spots at which the delivery actually takes place. Thus, there is a potential for optimization in the last mile of the whole process. To make the daily job of the postman better, VanAssist focus on this last mile. To exploit this potential, VanAssist aims to develop an integrated vehicle and system technology that enables largely emission-free and automated delivery of goods in urban centers. Consider a city pilot who is able to head to positions without any driver on board where the presence of the postman is not necessary. But to be able to achieve this vision, a lot of work in the field of safety assurance has to be done. Automotive vehicles are classified in a taxonomy by the Society of Automotive Engineers in the levels 0 to 5, where 0 means that there is no automation and 5 means fully automated. In between, at least some parts are automated, which more and more reallocates the responsibility from the human to the automated vehicle. Following the taxonomy, the city pilot is located at SAE level 4. This means that the presence of a human is not necessary. On board, he acts more like a passenger. To fulfill this, several driving conditions need to be met. For instance, that the automated vehicle is only allowed to drive in a city and not on a highway. But what if the vehicle is going to leave the city? Then the operational condition would not met. For example, if the depot is located outside of the city, in this case, the vehicle can request so that the human should continue the operation by transferring the responsibility to the human. But the human does not need to respond, which transfers the responsibility back to the automated vehicle. In this case, the vehicle will move into a safe state by its own, for instance by driving to the side strips and then stopping. It can be seen that monitoring the operational design domain is absolutely necessary, which leads to our first research question: how can the operational design domain monitored at runtime? Even if a human driver in an automated vehicle in SAE level 4 is not necessary in general, it is not debarred that a human driver can take over in case the automated vehicle cannot handle a situation. In this case, the responsibility is transferred to the human. Once a responsibility transfer is intended to be done, it has to be done in a dependable manner. This leads to our next research question: how can a dependable transfer of responsibility between the automated vehicle and the human driver be established? Until now, we considered a human as a passenger, but a human on board who always needs to help if the vehicle is having a problem will not help to optimize transport and logistic processes. But to able to optimize this process, the goal of VanAssist is to remove the human on board by a so-called off-board safety driver. The imagination is that there is a remote command control center in which multiple off-board safety drivers are helping automated vehicle to come out of problems remotely. This would allow also the supervision of a whole fleet, so that relation of one human supervises one vehicle is not necessary anymore. Because the off-board safety driver acts remotely, for instance from a different country, the on-site distribution has to be considered in a dependable transfer of responsibilities. This leads to our next research question: how can a dependable transfer of responsibility between the automated vehicle and the off-board safety driver be established? An off-board safety driver could supervise multiple automated vehicles, but once more than one automated vehicle is having a problem, the off-board safety driver will be overloaded because he can only help one automated vehicle at the same time. Thus, a mechanism to adequately coordinate the responsibilities between automated vehicle and remote safety driver has to be introduced. This leads to our last research question: How can responsibilities between automated vehicle and off-road safety driver be adequately coordinated, in particular in asymmetric circumstances? To demonstrate the results of the VanAssist project, we set up a lab consisting of a remote command control center, model vehicle, and VanAssist similar environment. The first mission for the autonomous vehicle is to drive from the parking lot to the depot to get loaded with the delivery packages. At the start of the day, the logistics center sends the list of mission to command and control center. The command control center operator assigns the list of mission to an available autonomous vehicle. Then the operator activates the first mission and sets the driving mode to fully autonomous driving. This causes the autonomous vehicle to drive from the parking lot to the depot. Finally, the autonomous vehicle arrives at the depot to get loaded with packages, which completes the first mission. The second mission for the autonomous vehicle is to drive from the depot to the postman's home to pick him up. First, the command control center operator activates the second mission for the autonomous vehicle. Then the autonomous vehicle drives from the depot to the postman's home. Finally, the autonomous vehicle arrives at the postman's home to pick him up, which completes the second mission. The next mission for the autonomous vehicle is to drive with the postman as a passenger from his home to the first drop-off point. After the command control center operator has activated the mission, the autonomous vehicle starts driving from the postman's home toward the first drop-off point. By arriving at the first drop-off point, the autonomous vehicle completes the third mission. Then the postman takes the first set of delivery packages for the first delivery route. The fourth mission for the autonomous vehicle is to drive to the meetup point at the end of the first delivery route to hand over to the postman the packages for the second delivery route. After the command control center operator has activated the mission, the autonomous vehicle starts driving from the first drop-off point to the first meetup point. Due to the pedestrian zone, the autonomous vehicle and the postman have to take different routes to the meetup point. But because of the road narrowing, the autonomous vehicle triggers an emergency stop. The next step is for the command control center operator to remotely analyze and solve the problem so that autonomous vehicle can continue the mission. First, the command control center operator gets informed about the emergency stop of the autonomous vehicle. After remotely analyzing the situation, the command control center operator reconfigures the autonomous vehicle to limited autonomous driving, which limits the driving speed but uses a smaller safety distance. During limited autonomous driving, the operator remotely observes the autonomous action of the vehicle. In case a safety risk emerges, the operator may remotely trigger an emergency stop. Under the observation of the remote operator, the autonomous vehicle can now continue its mission to drive to the meetup point at the end of the first delivery route. Finally, the autonomous vehicle arrives at the meetup point, completing the mission. When the postman arrives, he takes a second set of packages for the second delivery route. The fifth mission for the autonomous vehicle is to drive to the meetup point at the end of the second delivery route to pick up the postman. First, the command control center operator activates the fifth mission of the autonomous vehicle and reconfigures the driving mode to fully autonomous driving. Then the autonomous vehicle starts driving toward the first meetup point. But suddenly, a person playing ball enters the road in front of the autonomous vehicle, causing it to trigger an emergency stop. The next step is for the remote operator to analyze and solve the problem so that autonomous vehicle can continue its mission. After being informed about the emergency stop, the command control center operator remotely analyzes the situation and waits until the person with the ball has left the road. Then the remote operator reconfigures the autonomous vehicle back to fully autonomous driving. This enables the autonomous vehicle to continue its mission to drive to the meetup point at the end of the second delivery route. Finally, the autonomous vehicle arrives at the meetup point, completing the fifth mission. But while waiting for the postman, an unplanned event occurs. Due to leaves falling on the camera, the autonomous vehicle triggers an emergency stop to block driving. The command control center operator gets informed about this emergency stop. Remotely analyzing the situation, the operator recognizes that the front camera is blocked. Because this cannot be solved remotely, the operator prompts the postman via phone to solve the problem locally. After completing the second delivery route, the postman arrives at the autonomous vehicle. The postman removes the leaf and informs the command control center operator that the problem is solved. Now the remote operator can switch the driving mode back to fully autonomous. Can you please remove something from camera?
Yeah, okay, I can do it.
Okay, just inform me after removing it.
Okay.
The last mission of the day is for the autonomous vehicle to drive from the meetup point back to the parking lot with the postman as a passenger. First, the command control center operator activates the mission. Then the autonomous vehicle drives to the parking lot. And by arriving at the parking lot, autonomous vehicle completes the final mission and the postman can leave toward his home.